The Ford 10R140 is a heavy-duty 10-speed automatic transmission that represents Ford's attempt to create a robust transmission for their most demanding applications. This transmission features 10 forward speeds and is specifically engineered for high-torque applications in Ford's Super Duty truck lineup. The 10R140 is used across Ford's Super Duty truck range, including the F250, F350, F450, and F550 models. However, despite its advanced design and intended durability, the 10R140 has developed a concerning reputation for frequent failures and reliability issues. These issues have led to multiple recalls, lawsuits, and significant customer complaints, making the 10R140 one of the most problematic transmissions in Ford's recent history. From a mechanical engineering perspective, we will explore the technical reasons behind these failures, examining design decisions, manufacturing processes, and the complex interactions that contribute to the 10R140's reliability problems. The Ford 10R140 transmission represents a pinnacle of automotive engineering complexity. To understand why this transmission experiences so many issues, we must first examine the intricate design that makes it both powerful and problematic. The 10R140's complexity becomes apparent when we examine its technical specifications. This transmission contains 10 forward speeds and 1 reverse speed, requiring precise coordination between multiple systems. The heart of this complexity lies in its 4 planetary gear sets and 6 friction clutches. Each planetary gear set contains multiple gears that must work in perfect harmony, while the 6 friction clutches engage and disengage to create different gear ratios. Let's explode this transmission to see its internal complexity. The 4 planetary gear sets are arranged in sequence, each containing a sun gear, planet gears, and a ring gear. These components must mesh precisely to transfer power efficiently. Below the planetary gear sets are the 6 friction clutch packs. These clutches engage and disengage in precise combinations to create the 10 different forward gear ratios. Each clutch pack contains multiple friction discs that must apply exactly the right pressure at exactly the right time. To understand why complexity matters, let's compare the 10R140 to a simpler 4-speed transmission. A traditional 4-speed has only 2 planetary gear sets, 3 clutch packs, and approximately 50 moving parts. In contrast, the 10R140 has 4 planetary gear sets, 6 clutch packs, and over 200 moving parts. This dramatic increase in complexity provides more gear ratios for better fuel economy and performance, but it also creates exponentially more opportunities for something to go wrong. Each additional component introduces new potential failure modes. When you multiply the number of planetary gear sets, clutch packs, and control systems, you create a transmission that, while capable of impressive performance, is inherently more susceptible to problems than its simpler predecessors. The valve body represents one of the most critical and problematic components in the Ford 10R140 transmission. Understanding its complexity helps explain why so many transmission failures originate here. The valve body is essentially the brain of the transmission, a hydromechanical control unit that manages all hydraulic functions. It contains dozens of precisely machined passages, valves, and electronic components working in perfect coordination. Inside the valve body are numerous hydraulic passages that route transmission fluid to different clutch packs and components. These passages must maintain precise pressure and flow rates for proper shifting. Electronic solenoids control the hydraulic valves, acting as precise switches that open and close fluid passages. The 10R140 uses multiple solenoids to manage its 10 forward gears and complex shift patterns. However, this complexity creates vulnerability. Internal cross-leakage occurs when hydraulic fluid bleeds between passages that should remain isolated. This disrupts the precise pressure control needed for smooth shifting. Solenoid failures are particularly common in the 10R140. These electronic components can suffer from electrical issues, contamination, or mechanical wear, leading to erratic shifting, harsh engagement, or complete transmission failure. When valve body components fail, the transmission loses its ability to properly control hydraulic pressure and flow. This results in the harsh shifts, delayed engagement, and unpredictable behavior that many 10R140 owners experience. The valve body's hydromechanical complexity, while enabling the 10R140's advanced shifting capabilities, also makes it the transmission's most vulnerable component. Many transmission rebuilds focus specifically on valve body restoration and upgrade. The Ford 10R140 transmission uses a clutch-to-clutch design, which represents a fundamental shift from older transmission architectures. Understanding this design is crucial to comprehending why the 10R140 experiences many of its reliability issues. Traditional automatic transmissions used a combination of clutches, bands, and servos to control gear engagement. This distributed the mechanical stress across multiple types of components. In contrast, the 10R140's clutch-to-clutch design eliminates bands and servos entirely. All gear engagement is handled exclusively by clutch packs, which must bear the full mechanical load. This design change creates a critical weakness. With no bands or servos to share the load, each clutch pack must handle significantly more stress during gear changes and power transmission. Each clutch pack contains multiple friction plates that must engage and disengage under extreme pressure. In the clutch-to-clutch design, these components experience constant cycling and high stress levels. Under heavy loads, such as towing or aggressive driving, these clutch packs experience extreme pressure from all directions. This constant stress leads to accelerated wear of the friction materials. This design weakness manifests in several failure modes that are characteristic of the 10R140 transmission. The clutch-to-clutch design leads to several specific failure patterns. Clutch plates burn and glaze from excessive heat. Friction materials wear prematurely due to constant high stress. Clutch packs begin to slip under heavy loads, and heat causes component distortion that reduces the transmission's holding capacity over time. This design weakness is particularly problematic for Ford Super Duty trucks, which are often used for heavy towing and demanding applications. The clutch-to-clutch architecture simply cannot handle these loads as reliably as traditional designs with multiple load-sharing components. The Ford 10R140 transmission relies heavily on multiple solenoids to control its complex shifting operations. These electromagnetic devices are critical control components, but they represent significant vulnerability points in the transmission system. The 10R140 contains numerous solenoids positioned throughout the valve body. Each solenoid controls specific hydraulic circuits that manage gear engagement, shift timing, and torque converter lockup functions. To understand solenoid vulnerabilities, we need to examine their internal construction and operation. A typical transmission solenoid consists of an electromagnetic coil, a movable plunger, and a precision valve assembly. Solenoids are vulnerable to electrical failures, including coil burnout, short circuits, and open circuits. These electrical issues can cause complete solenoid failure or erratic operation, leading to unpredictable transmission behavior. Beyond electrical issues, solenoids suffer from mechanical wear within their valve bores. The precision fit between the plunger and valve bore is critical for proper hydraulic control. Over time, the constant movement of the plunger wears the valve bore, creating excessive clearance. This wear allows hydraulic fluid to leak past the valve, reducing control precision and causing erratic shifting behavior. When solenoids malfunction due to electrical or mechanical issues, the transmission experiences multiple performance problems that directly impact vehicle operation and driver safety. Erratic shifting patterns occur when solenoids provide inconsistent hydraulic pressure. Delayed engagement happens when worn solenoids cannot build pressure quickly enough. Harsh shifts result from solenoids that cannot modulate pressure smoothly, and in severe cases, the transmission may become stuck in a single gear when multiple solenoids fail simultaneously. Solenoid vulnerabilities represent a fundamental weakness in the 10R140 design. The transmission's reliance on multiple precision solenoids creates numerous failure points that can compromise overall transmission performance and reliability. Ford's adaptive transmission shift strategy was designed as an intelligent system to optimize shift quality over time. However, this sophisticated approach has introduced its own set of problems that affect transmission performance. The adaptive learning system, continuously monitors driving patterns, engine load, throttle position, and other parameters. It then adjusts shift timing and pressure to optimize performance for each individual driver and driving condition. The first major problem is inconsistent learning. Instead of developing smooth, predictable shift patterns, the adaptive system often creates erratic behavior. The transmission may shift differently under identical conditions, confusing both the driver and the system itself. As transmission components wear over time, the adaptive system receives increasingly inaccurate sensor data. Worn valve bodies, degraded solenoids, and internal leakage create noise in the system's feedback loop, leading to poor adaptive decisions. When multiple drivers with different driving styles use the same vehicle, the adaptive system becomes confused. It cannot distinguish between an aggressive driver who wants quick shifts and a conservative driver who prefers smooth, economical operation. The adaptive learning system, while innovative in concept, has become a significant source of problems in the 10R140. It creates unpredictable behavior that worsens over time and often requires dealer intervention to reset or reprogram the system. The CDF drum represents one of the most critical failure points in the Ford 10R140 transmission. This component houses three essential clutch packs, the C, D, and F clutches, which are vital for proper gear engagement and power transmission. Inside the CDF drum, the C, D, and F clutch packs work together to control different gear ratios. The steel sleeve that houses these clutches must maintain precise positioning to ensure proper hydraulic pressure and clutch engagement. To better understand this failure mechanism, we need to examine the internal structure. This cross-sectional view reveals how the steel sleeve fits within the drum housing and the critical tolerances involved. Under normal operating conditions, the steel sleeve maintains its proper position within the drum housing. This allows hydraulic fluid to flow correctly through oil passages, ensuring adequate pressure for clutch engagement. However, due to inadequate design tolerances and manufacturing precision, the steel sleeve can shift from its intended position. This movement is often caused by thermal expansion, wear, or insufficient clearance specifications during manufacturing. When the steel sleeve moves out of position, it can block critical oil passages within the drum. This disrupts hydraulic pressure to the clutch packs, causing erratic shifting behavior and, in severe cases, complete transmission failure. This CDF drum failure is particularly problematic because it affects multiple clutch packs simultaneously. When the C, D, and F clutches cannot engage properly, the transmission loses its ability to maintain gear ratios, resulting in a complete loss of drive power. The root cause of this failure often traces back to manufacturing tolerances that are too loose, allowing excessive movement, or design specifications that don't account for real-world operating conditions, including thermal cycling and mechanical stress. The E-clutch assembly represents one of the most problematic components in the Ford 10R140 transmission. This critical clutch pack suffers from a fundamental design flaw that makes it particularly vulnerable to failure. The primary issue stems from the E-clutch's role in the transmission's gear ratios. This clutch experiences an extremely high torque multiplication factor, meaning it must handle significantly more torque than what enters the transmission. Compounding this problem is the E-clutch's relatively small surface area. Let's compare the clutch surface areas to understand why this creates such a critical weakness. This combination of high torque multiplication and small surface area creates a perfect storm for clutch failure. The excessive pressure per square inch generates dangerous levels of heat and accelerated wear. Under heavy towing conditions, these problems become even more severe. The additional load dramatically increases the torque demands on the E-clutch, accelerating the failure process and often leading to complete transmission breakdown. The E-clutch assembly's design represents a critical engineering compromise that prioritizes compactness over durability. This fundamental flaw makes it one of the most frequent failure points in the 10R140 transmission, particularly affecting owners who regularly tow heavy loads. The oil pump is a critical component in the 10R140 transmission, responsible for maintaining proper oil pressure throughout the system. However, This pump has a significant weakness that becomes apparent under high RPM conditions. Under normal operating conditions, the oil pump maintains adequate pressure to lubricate all transmission components and operate the hydraulic control systems. The pump works by rotating internal gears that create suction and pressure. At normal RPMs, oil flows smoothly through the pump, maintaining consistent pressure. The blue particles represent oil flowing from the sump through the pump and into the transmission's hydraulic circuits. Problems arise when the engine operates at high RPMs, particularly during heavy towing operations. The increased engine speed places additional demands on the oil pump that it struggles to meet. At high RPMs, the oil pump can experience cavitation, the formation of vapor bubbles in the oil. This occurs when the pump tries to move oil faster than it can be supplied, creating low-pressure areas where the oil vaporizes. The pressure loss from oil pump problems leads to two major consequences. First, erratic shifting occurs as the valve body cannot maintain consistent hydraulic pressure to operate the clutches smoothly. Second, inadequate lubrication causes accelerated wear and potential damage to internal components. Clutches, bands, and other friction materials suffer when oil pressure drops below critical levels. The root cause is that the oil pump design cannot maintain adequate flow at high engine speeds. Cavitation reduces the pump's effective capacity, pressure drops below the minimum threshold, and the entire hydraulic control system becomes unreliable. This oil pump weakness is particularly problematic for truck owners who regularly tow heavy loads or operate in demanding conditions where sustained high RPMs are common. The transmission's reliability suffers significantly under these real-world operating conditions. Material selection plays a critical role in transmission durability. The Ford 10R140's reliability issues can often be traced back to inadequate material choices and insufficient heat treatment processes for the demanding conditions these transmissions face. When materials are subjected to stress beyond their design limits, they reach a failure point where structural integrity is compromised. In the 10R140, several components operate dangerously close to these failure thresholds. The CDF drum bushing is a critical component that has been identified as a major failure point. This bushing is made from materials that are insufficient for the high-stress, high-temperature environment of heavy-duty transmission operation. When the bushing material degrades under stress, it can slip from its proper position, blocking the critical oil passage. This blockage starves the clutch packs of lubrication, leading to catastrophic transmission failure. Heat treatment is crucial for developing the proper material properties needed for transmission components. The 10R140's bushing materials appear to have received inadequate heat treatment, resulting in insufficient hardness and poor wear resistance. Properly heat-treated materials develop a refined grain structure with improved hardness and thermal stability. This enhanced material structure is essential for withstanding the extreme conditions in heavy-duty transmission applications. Heavy-duty transmission applications subject components to extreme conditions that standard automotive materials may not be designed to handle. High temperatures, pressures, and millions of loading cycles create a perfect storm for material failure. When materials are not properly selected or treated for these demanding conditions, degradation accelerates rapidly. This leads to premature component failure, often manifesting as the bushing slippage and oil blockage issues seen in the CDF drum assembly. The material selection and heat treatment issues in the Ford 10R140 transmission represent fundamental engineering compromises that have significant real-world consequences. Addressing these material deficiencies is essential for improving transmission reliability and longevity. The Ford 10R140's pursuit of 10 forward speeds came at a significant cost to overall robustness. When compared to earlier, simpler transmission designs, the 10R140 sacrifices the proven durability that made previous generations reliable workhorses. Traditional 4-speed automatics were built with simplicity and durability in mind. With approximately 150 components and proven designs, these transmissions could reliably handle decades of heavy use with minimal maintenance. In contrast, the 10R140 contains over 400 individual components, including multiple planetary gear sets, 6 friction clutches, and numerous solenoids. This complexity creates exponentially more potential failure points and reduces overall system robustness. The fundamental issue lies in the engineering trade-offs made during the 10R140's development. The relentless pursuit of 10 forward speeds forced engineers to prioritize complexity over the time-tested principles of robust mechanical design. Traditional transmission design emphasized robust construction with generous safety margins and proven materials. Components were sized larger than strictly necessary, ensuring they could handle stress well beyond normal operating conditions. The 10R140's design philosophy prioritizes packaging efficiency and performance metrics over long-term durability. Components are sized to minimum specifications, leaving little margin for the real-world stresses of heavy-duty applications. The 10R140's fundamental lack of robustness represents a critical engineering misstep. While 10 speeds may sound impressive, this complexity came at the expense of the proven durability principles that made previous generations of transmissions reliable for hundreds of thousands of miles. Manufacturing tolerances and quality control play a critical role in transmission reliability. Even microscopic variations from specified dimensions can cascade into major failures in complex systems like the Ford 10R140. Manufacturing tolerance refers to the acceptable range of variation in a component's dimensions. Every part has a target dimension, plus or minus a small allowable deviation. This means the shaft can measure anywhere from 49.95 to 50.05 millimeters and still be acceptable. However, in complex assemblies, these small variations can accumulate and cause problems. In the 10R40 transmission, multiple components must fit together precisely. When tolerances stack up, small individual variations can create significant assembly problems. When all tolerances stack in the worst-case direction, the total variation can be much larger than any individual component tolerance. This can cause binding, excessive clearances, or complete assembly failures. Quality control systems are designed to catch these variations before they reach customers. However, the complexity of the 10R140 makes comprehensive testing challenging and expensive. Critical measurements in the 10R140 include valve body bore diameters, clutch pack clearances, and gear tooth spacing. Even tiny deviations in these dimensions can affect hydraulic pressure, shift timing, and component wear. When manufacturing tolerances are not properly controlled, a cascade of failures can occur. A slightly oversized valve bore leads to pressure loss, which causes delayed shifts, increased heat, and ultimately clutch failure. This demonstrates why manufacturing precision is so critical in complex transmissions. What starts as a microscopic dimensional variation can ultimately result in complete transmission failure and expensive repairs for vehicle owners. The Ford 10R140 transmission is primarily found in Super Duty trucks designed for demanding applications like towing heavy trailers and hauling substantial loads. These demanding conditions place extraordinary stress on every component within the transmission, from the clutch packs to the valve body and hydraulic systems. 3 primary factors accelerate transmission wear during heavy use: extreme operating temperatures, massive torque loads, and prolonged periods of high-stress operation. High operating temperatures, often exceeding 220 degrees Fahrenheit during heavy towing, cause transmission fluid to break down, seals to deteriorate, and metal components to expand beyond design tolerances. The transmission must multiply engine torque by up to 4 times in first gear. When towing heavy loads, this can result in output torque exceeding 1,900 pound-feet, placing enormous stress on clutch packs and internal components. Heavy towing and constant high-load operation can reduce transmission lifespan by nearly half, with failures commonly occurring around 80,000 miles compared to 150,000 miles under normal driving conditions. These demanding operating conditions expose the fundamental design limitations of the 10R140, making it particularly vulnerable to the mechanical stresses that heavy-duty truck owners regularly encounter. While the 10R140 transmission has inherent design weaknesses, proper maintenance plays a crucial role in determining how quickly these problems manifest and how severely they impact the transmission's performance. Regular maintenance intervals are critical for the 10R140. Ford recommends transmission fluid changes every 30,000 miles under normal conditions, but severe duty applications like frequent towing may require more frequent service intervals. The quality and specification of transmission fluid is paramount. Fresh fluid maintains proper viscosity, provides adequate lubrication, and contains additives that protect internal components from wear and corrosion. As transmission fluid degrades over time, it loses its protective properties. Degraded fluid becomes contaminated with metal particles, loses viscosity, and can no longer provide adequate protection for the transmission's complex internal components. Neglecting maintenance doesn't create the 10R140's design flaws, but it dramatically accelerates their progression. Poor maintenance can turn a transmission that might last 150,000 miles into one that fails at 80,000 miles or less. Proper maintenance of the 10R140 requires attention to specific details. Using the correct Mercon ULV fluid specification is essential, as is replacing the filter during fluid changes and maintaining proper fluid levels. While proper maintenance cannot eliminate the 10R140's inherent design weaknesses, it significantly extends the transmission's service life and delays the onset of major problems. Regular maintenance is the most cost-effective way to maximize the transmission's reliability. The widespread failures of the Ford 10R140 transmission have created a thriving aftermarket industry focused on addressing the transmission's known weaknesses through upgraded components and improved designs. Aftermarket manufacturers have identified the primary failure points and developed upgraded parts that significantly improve reliability. These solutions focus on three critical areas: the valve body, clutch assemblies, and the problematic CDF drum. Valve body upgrades represent one of the most significant improvements available. Aftermarket valve bodies feature tighter bore tolerances, improved solenoid designs, and better materials that prevent the cross-leakage issues plaguing the original equipment. Clutch material upgrades, particularly Raybestos GPZ friction plates, offer significant improvements over original equipment. Testing shows these materials can outperform OE components by up to 20% while providing better heat resistance and extended service life. CDF drum reinforcement addresses one of the most critical failure points. Aftermarket solutions include hardened outer shells, improved bushing designs, and better oil flow channels that prevent the bushing slippage and oiling blockages that cause catastrophic failures. These aftermarket upgrades collectively transform the 10R140 from a problematic transmission into a much more reliable unit. By addressing the fundamental design weaknesses through improved materials and engineering, these solutions significantly reduce failure rates and improve performance, especially under heavy-duty applications. The valve body is often called the brain of the transmission, and upgrading it represents one of the most critical improvements for the 10R140. Understanding why these upgrades are so important requires examining both the problems with the original design and the solutions that aftermarket manufacturers provide. The valve body serves as the hydraulic control center of the transmission. It contains numerous valve bores, passages, and solenoids that direct pressurized fluid to engage and disengage clutches. In the 10R140, this complex component is prone to several critical failures. The original valve body suffers from several key problems. Cross-leakage occurs when valve bores wear and allow fluid to leak between circuits. Solenoids fail due to electrical issues and contamination. These problems lead to erratic shifting, harsh engagement, and eventual transmission failure. Aftermarket valve body upgrades address these fundamental issues through improved materials, tighter tolerances, and enhanced solenoid designs. These upgrades represent a comprehensive solution to the 10R140's hydraulic control problems. Upgraded valve bodies feature precision-machined valve bores with tighter tolerances to eliminate cross-leakage. Enhanced solenoids provide more reliable electrical operation and better contamination resistance. Improved sealing technology and optimized flow characteristics ensure consistent hydraulic pressure control. The benefits of valve body upgrades are immediately noticeable. Drivers experience smoother shifting, more consistent engagement, and significantly improved reliability. These upgrades often eliminate the harsh shifts and erratic behavior that plagued the original 10R140 design. Valve body upgrades represent the single most effective modification for addressing 10R140 reliability issues. By solving the root cause of hydraulic control problems, these upgrades provide a foundation for long-term transmission performance and durability. One of the most effective ways to improve the Ford 10R140 transmission's reliability is upgrading the clutch friction materials. The original equipment materials have significant limitations that can be addressed with modern high-performance alternatives. The clutch pack assembly consists of alternating steel plates and friction plates. The friction plates are the critical components that determine the transmission's torque capacity and heat resistance. These friction plates are where the power transfer occurs. In the original equipment design, these plates use standard organic materials that have limited heat resistance and can degrade under high torque conditions. Let's compare the original equipment materials with the upgraded Raybestos powertrain GPZ friction plates. The differences in performance characteristics are substantial. The most significant improvement is heat resistance. While OE materials begin to degrade at around 300 degrees Fahrenheit, GPZ materials can withstand temperatures up to 450 degrees Fahrenheit, a 50% increase in thermal capacity. The improved friction coefficient means better power transfer efficiency and more consistent engagement. Testing has shown that GPZ materials can outperform original equipment materials by up to 20% in durability and torque capacity. The benefits of upgrading to high-performance clutch materials include increased torque capacity, better heat dissipation, reduced wear rates, and improved shift quality. These upgrades are particularly valuable for trucks used in heavy-duty applications like towing. Clutch material upgrades represent one of the most cost-effective improvements for the 10R140 transmission, providing significant performance gains and reliability improvements that address many of the transmission's inherent weaknesses. The CDF drum weakness in the Ford 10R140 transmission has prompted the development of comprehensive aftermarket solutions that address the fundamental design flaws found in the original equipment. The original equipment CDF drum suffers from a critical weakness in its bushing design. The steel sleeve can slip and block the oiling hole, leading to catastrophic clutch failure and complete loss of transmission function. Aftermarket manufacturers have developed significantly improved CDF drum designs that address these fundamental weaknesses through enhanced materials and reinforced construction methods. The material improvements in aftermarket CDF drums include the use of hardened steel alloys with advanced heat treatment processes, providing significantly greater resistance to wear and thermal stress. These aftermarket solutions incorporate several critical design improvements, including reinforced bushing retention systems, optimized oiling hole designs, enhanced clutch pack clearances, and significantly stronger shell construction. The reliability benefits of these aftermarket CDF drum upgrades are substantial, providing a 300% increase in bushing retention strength, complete elimination of oiling hole blockage issues, significant reduction in clutch pack burning incidents, and dramatically extended transmission service life. These comprehensive aftermarket solutions represent a fundamental improvement over the original equipment design, addressing the root causes of CDF drum failure and providing transmission owners with a reliable, long-term solution to this critical weakness. Ford Motor Company has implemented several strategies to address the persistent issues with the 10R140 transmission. These efforts have focused on both software improvements and hardware modifications. Ford's primary response involved releasing multiple software updates for the transmission control module. These updates aim to improve shifting logic, reduce sudden downshifts, and enhance the adaptive learning algorithms. Ford also implemented hardware modifications targeting the most problematic components. The CDF drum bushing received material improvements and better oil flow design, while the outer shell underwent hardening treatments to increase wear resistance. While Ford's efforts have resulted in measurable improvements, they have not completely eliminated the 10R140's problems. The software updates reduced the frequency of sudden downshifts and improved overall shift quality, but issues continue to persist in many vehicles, indicating that the underlying design challenges remain unresolved. These partial improvements demonstrate Ford's commitment to addressing customer concerns, but also highlight the complexity of the transmission's fundamental design issues that require more comprehensive solutions. The widespread reliability problems with Ford's 10R140 transmission have triggered significant legal consequences, including multiple recalls and ongoing class action lawsuits that highlight the severity of these issues. The most significant recall involved over 550,000 Ford F-150 trucks due to dangerous sudden downshifts into first gear without warning, creating serious safety hazards for drivers. Class action lawsuits are currently ongoing in both the United States and Canada, with consumers seeking compensation for unsafe vehicles and related expenses, including repair costs and diminished vehicle value. The legal actions represent thousands of affected vehicle owners who have experienced expensive transmission failures, safety concerns, and significant financial losses due to the 10R140's reliability problems. These recalls and lawsuits underscore the widespread nature and severity of the 10R140 transmission problems, highlighting the significant impact on consumer safety and the automotive industry's responsibility to address these critical reliability issues. For the 2025 model year, Ford made a significant strategic decision regarding their heavy-duty transmission lineup. This change represents a notable shift in their approach to addressing the ongoing 10R140 reliability concerns. Ford has transitioned from the problematic 10R140 transmission to the 10R100 transmission. This change specifically affects vehicles equipped with the 7.3-liter Godzilla engine in Ford's Super Duty lineup. This strategic shift represents Ford's acknowledgement of the 10R140's reliability issues and their commitment to providing a more dependable transmission solution for their heavy-duty applications. The 10R100 transmission is now specifically paired with Ford's 7.3-liter Godzilla engine across the Super Duty lineup. This includes the F250, F350, F450, and F550 models that utilize this naturally aspirated V8 power plant. This transmission change indicates Ford's recognition that the 10R140's design limitations made it unsuitable for continued use in certain high-demand applications. The move to the 10R100 represents an engineering decision to improve reliability and customer satisfaction. The shift to the 10R100 transmission demonstrates Ford's proactive approach to addressing transmission reliability concerns. This change specifically targets the heavy-duty applications where the 10R140's weaknesses were most problematic, showing Ford's commitment to engineering solutions that prioritize customer satisfaction and vehicle dependability. Looking ahead to the future of the Ford 10R140 transmission, the outlook presents both challenges and opportunities. As of early 2025, Ford has not announced any immediate successor to the 10R140, which means this transmission will continue to be used in Super Duty trucks for the foreseeable future. This extended service life means that current and future 10R140 owners will need to rely heavily on aftermarket solutions and diligent maintenance practices to ensure reliable operation. The aftermarket industry has responded to the 10R140's challenges by developing comprehensive upgrade solutions. These include improved valve bodies with better materials and tighter tolerances, enhanced clutch materials that can withstand higher torque loads, and reinforced CDF drum assemblies to prevent the common failure modes. Equally important is the role of preventive maintenance in extending transmission life. Regular fluid changes, proper servicing intervals, and monitoring of transmission behavior can significantly improve reliability. A comprehensive maintenance approach includes frequent fluid changes every 30 to 50,000 miles, regular filter replacements, transmission cooler inspections, staying current with software updates, and continuous performance monitoring to catch issues early. Looking forward, Further engineering improvements will be necessary to fully address the underlying design issues. This may include redesigned valve bodies with improved materials, enhanced clutch pack configurations, and better oil flow management systems. The path forward requires innovation in materials science, component redesign, and enhanced control systems. While the 10R140 will continue serving in Ford's heavy-duty lineup, its long-term success will depend on the industry's ability to address its fundamental weaknesses through both aftermarket solutions and potential factory improvements. After examining all aspects of the Ford 10R140 transmission, we can see that its frequent failures result from a complex web of interconnected issues, not a single design flaw. The transmission suffers from multiple critical failure points that compound each other's effects. Valve body issues, CDF drum failures, clutch problems, solenoid vulnerabilities, oil pump issues, and overall design complexity all contribute to the reliability problems. These failures stem from three primary contributing factors. First, the inherent design complexity of a 10-speed clutch-to-clutch transmission with multiple solenoids creates numerous potential failure points. Second, the demanding conditions of heavy-duty use, including towing, high-torque loads, and extreme operating conditions, stress the transmission beyond its design limits. Third, inadequate maintenance practices, including infrequent fluid changes, ignored warning symptoms, and delayed repairs, accelerate component wear and failure. While Ford has attempted to address these issues through software updates, recalls, and component modifications, their solutions often provide only partial fixes to the underlying problems. Aftermarket solutions, including valve body upgrades, enhanced clutch materials, and CDF drum reinforcements, often provide more comprehensive and durable fixes to the transmission's fundamental weaknesses. Regardless of the solution chosen, proactive maintenance remains absolutely critical for maximizing the 10R140's lifespan. Regular fluid changes, filter replacements, and comprehensive services can prevent many failures before they occur. In conclusion, the Ford 10R140 transmission represents a complex engineering challenge where multiple failure modes interact and compound each other. Success with this transmission requires understanding its inherent complexity and taking a proactive approach that combines proper maintenance with targeted upgrades where necessary.